All right, welcome to the full version of the section 1.5 summary from the OpenStax PreCalculus book. In this section, we're talking about function transformations, which is a hell of a topic, to be perfectly honest with you. It's a topic that gives a lot of students a lot of trouble. Because it gives students trouble, I've taught it in many different ways, trying to see what works best, and come up with something that I think works pretty well for me. So I'm going to go through this summary, teaching this the way I think it's easiest to understand it. I'll deviate slightly from the OpenStax book. I'll get all the same topics they have, just talk about them slightly different. But in order to not confuse people, I'll try to be really clear about where I deviate and how I deviate and explain the rationale for doing so. So at any rate, function transformations, there's really two topics. At the end of this video, we'll be talking about odd and even functions. I don't know, function transformations is 90% of this section, odd even functions is 10% if I had to quantify things. Function transformations. The first big difference between me and your book is your book will tell you there's 6 different function transformations. I'm like, nah, I'm good with 4. 6 sounds like a lot, let's stick to 4. I think that it's easier to think about these as 4 different types as opposed to 6 different types. I'll account for everything they account for. I just think it's easier to have less things to understand. And so the 4 types that the way I see it are there's 2 vertical transformations and 2 horizontal transformations. So by vertical, I mean things are happening up and down. And by horizontal, I mean things are happening left and right. And since we're talking about a graph, you may remember that on the x-coordinate, the left and right, we graph the inputs for a function. And on the y-coordinates, the up and down, we graph the outputs for a function. So all the vertical transformations, things that go up and down, are going to be affecting the output of a function, whereas the horizontal transformations are the things that are going to be affecting the input for a function. What are you talking about affecting input, output? Okay, let me start with an example. From section 1.1, you learned a bunch of toolkit functions, a bunch of simple functions that either you memorize the graph of or you understand the graph of, something like that. One of them is the function f of x equals x squared. That's what I've graphed in red here. F of x equals x squared. There's the same graph I have over here. Over here, I used f of x equals the absolute value of x, and over here, I got x cubed. So a few of our different toolkit standard functions that maybe you have memorized. And the idea in this section is, why do you bother memorizing 5 or 6 different graphs if there's infinitely many graphs out there? How often do you see just f of x equals x squared? Not x squared plus 3, or 5 times x squared, or 5 times x plus 1 squared, minus 7, something like that. Well, what we're going to do is we're going to understand what all those different numbers would do to the graph. So by just memorizing these kind of starting spots, and then how to transform the graph, we can come up with this huge, set of graphs. So really the idea is we'll come up with kind of families of graph. We'll come up with families of graphs that start out looking like this, but end up looking different depending on what we do to them. So for example, x squared minus 3. Maybe I give you this function g of x equals x squared minus 3, and I ask you to graph that. Well, it turns out you can graph that even though you don't have this entire graph memorized. All you have memorized is f of x equals x squared, but you might recognize that this is similar to f of x equals x squared. The only difference is I have this minus 3 tacked on at the end. And so what you want to recognize is that what I'm doing is subtracting in this case. It works for either adding or subtracting something from the output of the function. Wait, what do you mean the output of the function? Okay, so the original function I started with is x squared. And I have x squared minus 3, not x minus 3 squared. If I had x minus 3 squared, I'd be subtracting from the input, the x value. But I'm not. I'm subtracting from the output, the f of x value. So I have a vertical transformation here. Note that the general form here, I got f of x plus a, not f of x plus a. I'm not adding the a, or subtracting in this case, the a to the x value. I'm adding it to the f of x value. And so that's how you realize that you have this first type of transformation of vertical shift. And so all you have to do, well, okay, in your book, what it'll say is, for this specific example, we're going to shift this graph down by 3. And that's 100% true. However, I think it's easier to think of all of these in terms of operations. So what I'm going to do is focus on this column right here, although I just kind of made it hard to read. Whereas most books focus more on this over here. Most books like to describe what you're doing in terms of the graph, in terms of how it looks. And I think that although it's easier to start out thinking about it that way, when you get into more complicated examples, it'll be much easier to keep everything straight if you just remember the operation that's going on. So in this case, all I'm going to do is add whatever a is to all of my y coordinates. The y coordinates, because I have a vertical shift here. The y coordinates because I'm affecting the f of x value, which is the y. If it were f of x plus a, I'd be messing with the x coordinates. But it's not. It's f of x plus a, not f of x plus a. I hope you can tell the difference between those two based on how I said it. I'm talking about the difference between this first row and this third row. So in this case, I would first recognize that I have this type of transformation. And then I would say, all right, in this type of transformation, I add whatever a is to the y coordinates. So what is a in this general form over here? You might think it's 3, but it's not. It's actually negative 3. Because x squared minus 3 is the same as x squared plus negative 3. So what I'm going to do is I'm going to add negative 3 to each of the y coordinates. I'm going to go down here to my graph and recognize that the y coordinate right here was 0. And if I add negative 3 to 0, that's the same as subtracting 3, I would get a y coordinate of negative 3. Then I'll stare at this point. This point right here has a y coordinate, a height of 1. And if you add negative 3 to 1, you end up at negative 2. This y coordinate right here is 4. And if you add negative 3 to 4, you get down to positive 1. Similarly, this y coordinate is 1. Add negative 3 to that, you'll get negative 2. This y coordinate is 4. Add negative 3 to that, you'll get positive 1. So rather than shift the entire graph like a lot of books will say, I find points on the graph, 5 in this case, and I algebraically affect those points. So I add whatever a is to each of the y coordinates. And note, again, it's the y coordinates because I affected the output. This was x squared minus 3, not x minus 3 squared. That gives me these points in blue right here, which I can then connect with a curve that follows roughly the same shape as my original graph. And what I have is a graph of g of x equals x squared minus 3. I have this first type of transformation. The second type of transformation is similar to this first type in that I'm still affecting the output. So for example, I could have 2 times x squared. Okay, the first thing to note is this is not 2x squared. It's 2x squared. What I'm saying is the 2 is not being squared right here. Our order of operations squares the x and then multiplies by 2. So what I'm doing here again with this 2 is I'm affecting the output. I'm affecting the x squared. If I wanted to multiply the x by 2, it would have to look more like this with parentheses. Here I'm multiplying it by 1/2. Here I'm multiplying the x squared by 2. Because it's the output that's getting multiplied by 2, like I have written right here, I have another vertical transformation. In this case, it's a vertical stretch. The difference between vertical shifts and vertical stretches is vertical stretches happen when you have multiplication, when you're multiplying your f of x by something as opposed to adding something to your f of x. And what you do when you're multiplying here, maybe not surprisingly, is I'm going to multiply all of the old y coordinates by whatever b is. So b in this case is the number 2, positive 2. So what I'm going to do is take all the old y coordinates. This y coordinate was 0. 0 times 2 is still 0. So this y coordinate, this point's going to stay right here. This y coordinate was 1. 1 times 2 is 2. This y coordinate was 4. 4 times 2 is 8. That's way the hell up here off my graph. Okay, that's fine. 1 for this y coordinate times 2 leaves me at 2. And again, 4 times 2 for this y coordinate will be way up at 8. So I don't even have these points on my graph, but I can still kind of graph things, make my graph look more or less like this. In terms of words, what I just did here is I stretched my graph vertically, which is how most books will describe this. But I think it's a lot easier to think about this as you're just taking all the old y coordinates and you're multiplying them by whatever b is. The first big advantage to my way is if you just use the names, then if b is negative, it's going to have a very different effect. Your book is going to add on 2 more transformations here, and they're going to call them flips or reflections. And the idea is if this b is negative, they're going to say, oh, you reflect your graph over the x-axis. That's 100% true, but you don't even need to worry about that if you apply all the transformations according to the operations. Because, for example, if this were negative 2 times x squared, this would no longer just be a vertical stretch. It would be a vertical stretch and a vertical transformation or some sort of reflection. It would be hard for you to wrap your head around everything that's going on here. There'd really be 2 different things going on. But if you just think about them in terms of the operations, it's the exact same as the example I just did. I take all of the old y coordinates, and instead of multiplying them by 2, I'd multiply them by negative 2. So this one that was at 1, 1 times negative 2 is negative 2. Maybe I'll write this a little bit. As long as I have this graph here, let's show a graph of h of x equals negative 2x squared. So what I just graphed in blue was g of x equals 2 times x squared. You don't need this little dot in here, but I think it really emphasizes that the whole x squared thing is getting multiplied by 2, which is why this is a vertical transformation, not a horizontal transformation. So that's what I had in blue. In red, I had the original graph, f of x equals x squared. Supposing you had this in green here, most books would tell you to think about this as two different transformations. First deal with the 2, then deal with the negative. But I think if you follow this column right here, and all you do is multiply all your y coordinates by b, you stare at this y coordinate that had a height of 0. 0 times negative 2 is still 0, so this point stays right here. This y coordinate had a height of 1. 1 times negative 2 is negative 2, so it's going to go down here. Weird. Don't worry about it. It'll work out. This y coordinate was 4. 4 times negative 2 is negative 8, so that's way the hell down here. Fine, it's not even on my graph, so I'm not going to graph it, but keep that in the back of your mind that I have some point way the hell down here. This y coordinate was 1. 1 times negative 2 is negative 2. This y coordinate was 4. 4 times negative 2 is negative 8, so it's way down here. And my graph ends up looking like this, roughly speaking. The geometry of what I just did would take a while to explain. You'd have to say it was some sort of a stretch, and it was also some sort of a reflection, some sort of a flip. But as long as you just deal with this column, you don't have to worry about it as two different things. You can just say it's negative 2x squared. One last comment I want to make before I move on to horizontal transformations is that if the value of b is between 0 and 1, so instead of being 2 right here, this were 1/2, then all of a sudden vertical stretch doesn't make sense anymore. We'd call it a vertical, I don't know, compression maybe is the word a lot of books use. So now all of a sudden I have another row here for this reflection idea I did, and another name here for compressions when that's more appropriate than stretching, when I have some sort of fraction as my value of b and that fraction is between 0 and 1. Man, this is getting really complicated. I can see why I made such a big deal out of this at the start of the chapter. Okay, however, if you think about this just in terms of operations, you don't need extra rows. If this were 1/2 instead of 2, we'd just take all of our old y coordinates, these things in red here, and multiply them all by 1/2. No problem. This one that was in 1, was at 1, had a height of 1. 1 times 1/2 is just 1/2. It would go down here. This one that had a height of 4, 4 times 1/2 is 2, so it would go down here. My graph would end up looking kind of like this, and you could describe what I just did in terms of the graph as a vertical compression instead of a stretch. So maybe I'll even write stretch slash compression slash flip or reflection. But really the point that I'm making is you don't even have to worry about that. You don't have to worry about the fact that there's 3 different things that fit in here if you just deal with this column. Just multiply all of the old heights by whatever the value of b is, whether it's positive or negative or greater than 1 or less than 1. I don't care. Just multiply them all by b. That's all you got to do. It's my way anyways. So that's vertical transformations. The nice thing about vertical transformations is they follow a lot of intuition. When you see a plus a here, you add whatever a was. If it was minus some number here, like -3, well, then you end up subtracting 3. You do everything exactly like you would expect to do. If there's a 2 here that you're multiplying the x squared by, you multiply all the heights by 2. If this value were -3, you'd multiply all the heights by -3. If it were 1/2, you'd multiply all the heights by 1/2. What we'll see later is that we could have more than one of these transformations at a time. So I could have a vertical shift and a vertical stretch. Oh man, that would be all sorts of confusing, right? What if I had g of x equals 2x squared and then a +5 or something? Then I'd have both this first type and this second type. And it turns out the order you apply your transformations is really, really important. We'll talk about those examples later, but the point I want to make before I move on from vertical is everything with vertical is nice. If I asked you which one, if you had 2 of these, would you apply first, you might guess using your order of operations that you do multiplication before addition and subtraction. And you know what? You'd be right. You have to apply this type of transformation before this type. And it makes sense. Everything with vertical transformations is logical. That's the good news. The bad news is now I'm going to talk about horizontal transformations, and unfortunately, nothing with horizontal transformations makes sense. Everything is backwards. Everything is the opposite of what your intuition would tell you. The reason that happens is because we're affecting the input when we're dealing with horizontal transformations. So we're making changes before the machine can do its thing. So if you think about what would come out of the machine, you have to account for the fact that you changed things before it went into the machine, and it ends up kind of flipping everything around in some sense that I'll try to make more clear when I go through these examples. So now, really in my head, I think about there's a big split right here. There's two vertical transformations, which are the types I've talked about before. Books will tell you there's four, I say there's two. There's the ones where you add, and there's the ones where you multiply. And now I'm going to talk about horizontal transformations. The good thing, I suppose, about horizontal transformations is there are some parallels between vertical and horizontal transformations. So once you get the hang of vertical transformations, horizontals aren't that bad. The other thing that's kind of nice, I suppose, about horizontal transformations is that even though they're unintuitive, they're always unintuitive. If you're going to be bad, at least consistently be bad, so I know to expect it to be bad. That's what's going to happen here. The first type of horizontal shift, or horizontal transformation that I'm going to talk about is a horizontal shift. And much like the vertical shifts, it happens when you have addition or subtraction going on here. So if you look at the general form up here, I had a vertical shift when I added some number to the output of the function. I'm going to have a horizontal shift when I add some number to the input of the function. So here I'm adding it to the x, here I'm adding it to the f of x. Because I'm adding it to the x here, it's going to affect the x coordinate, not the y coordinate. So it's going to move things left and right instead of up and down. So an example would be the absolute value of x plus 1. Don't confuse this with the absolute value of x plus 1. If this were the absolute value of x plus 1, then it would be this type of shift up here, and I'd move everything up by 1. But it's not. It's the absolute value of x plus 1, so this is not a vertical shift, it's a horizontal shift. When you have a horizontal shift, you got bad news. The value of a, you're not going to add it to all of your x coordinates. You're going to instead subtract it from your x coordinates. Why? It's a good question. I just complimented myself for a question that I asked myself. That was a pretty stupid thing to do. Okay, why is everything backwards? I'll try to explain why it's backwards later. I'll give you an example. But I think, to be perfectly frank, it's best to just memorize that everything that has to do with horizontal transformations is the opposite of what you'd expect. So when you see this plus 1 right here, that does not mean add 1 to all of the x coordinates. It means subtract 1 from all of the x coordinates. If you had the absolute value of x minus 5, you might immediately think that it means subtract 5 from all of the x coordinates, but it doesn't. It means add 5 to all of the x coordinates. The way you can keep it straight is you're always subtracting whatever a is. So if a is positive, you're subtracting a positive number. If a is negative, you're subtracting a negative number, which is the same as adding. Okay, I'm giving you too many examples at once. Let's write some stuff down here. This graph, what does this look like? Well, the way I would do it, rather than think about it as a shift, although it is a shift, I'm going to shift this entire graph to the left by 1 unit. Rather than think about it like that, I'm going to think about it in terms of the operations. Even though it might be easier to initially think about it as a shift, I think it'll pay dividends in the long run to think about it as I'm just going to subtract a, which is positive 1 in this case, from all of my old x coordinates. The x coordinate right here is 0. Remember, the x coordinate is how far left and right you are. If you subtract 1 from 0, you're at negative 1. The x coordinate right here is negative 1. If I subtract 1 from negative 1, I'm at negative 2. The x coordinate right here is negative 2. If I subtract 1 from negative 2, I'm over here at negative 3, and so on. And you're like, oh, right, everything just shifts one spot to the left. Yes, that's true, but try to get into the habit of thinking about it in terms of the operation. It'll pay dividends later on. Don't think about it in terms of this column, think about it in terms of this column. You took all of the old x coordinates. The x coordinate right here is 3, and you subtracted 1 to get 2. And now I'm going to connect all the blue dots with a line that has roughly the same shape as my red graph. And what I have here is a graph of g of x equals the absolute value of x plus 1. I should have said that quicker. The absolute value of x plus 1. And this graph was f of x equals the absolute value of x. This is a good point for you to think about, wait, what would have happened if it were the absolute value of x, and then outside of the absolute value signs there was a plus 1? And if you can see what that graph would look like in blue, that's fantastic. First of all, it wouldn't have been over here because it wouldn't have been a horizontal shift, it would have been a vertical shift. And so it wouldn't go to the left by 1, it would have gone up by 1. It would look something like this. But it's not, so don't worry about that. I could do more examples while I'm here, but I think I'm going to push on and talk about the last type of transformation. And again, your book will tell you that there's more than 4 types of transformations, and nothing against your book. I think you got a great book. Definitely got the price right on your book. But most texts talk about more types of transformations, and I just think that confuses students. I think it's a lot easier to just think about there's 2 types of horizontal transformations. We just talked about one of them. Now we're going to talk about the other one. And what we do with the next type, it parallels this second type right here. So remember, this type occurred when the output, the f of x, got multiplied by some number. So here the output, which was x squared, is getting multiplied by 2. So I'm going to take all of the old heights and multiply them by 2. Similar here, except now it's the input that's getting multiplied by 1/2. The input is being multiplied by 1/2 in this case. Because it's the input, the x-coordinate, that's being multiplied by 1/2. I don't have a vertical stretch, I have a horizontal stretch. And because everything's goofy with horizontal, I'm not going to multiply all of my old x-coordinates by b. I'm going to instead divide all my old x-coordinates by b. Whoa, so you're going to divide by, let's see, what's playing the role of b here? I guess b would be 1/2 because it's supposed to be b times x in this general case. So this is 1/2 times x. So I have to divide by 1/2. Think about that for a minute. What do you get when you divide by 1/2? If I have a number like 5 and I divide 5 by 1/2, dividing by 1/2 is the exact same as multiplying by 2. So yes, a lot of books will tell you that what you do in this case is you multiply it by 2. But rather than get confused on the operation, wait, am I multiplying this time or am I dividing this time? I think it's a lot easier to remember that you always divide here. It's just sometimes you'll be dividing by fractions. Spend some time, invest some time, and learn how to divide by fractions if you don't already. And then you don't have to keep straight which operation you're using, multiplication or division. Anytime you're down here in this horizontal stretch case, you're always dividing. Just dividing by whatever this number is. If I gave you g of x equals x divided by 2 cubed, that looks confusing, but all you got to do is write it in this form. All you got to do is recognize that that's really just 1/2 times x cubed. And so when you see this, don't think about b as 2, but now it's division instead of multiplication, and there must be some other case that I have to memorize. Instead, recognize that this is this. And so really, I just have this exact same problem that I just had. The value of b is 1/2, so I'm going to divide by 1/2. And dividing by 1/2 is the same as multiplying by 2. Okay, that was a quick refresher on dividing fractions. Let's actually see that in play in terms of our graph. This starts out with the graph of x cubed, which is what I have in red right here. Maybe I should label it. This is f of x equals x cubed. I highlighted 3 points on this graph. You don't have to pick these 3, but I think these 3 will give us a decent idea of how the rest of the graph looks. And then in blue, what I'm going to try to do is sketch a graph of g of x equals 1/2 x cubed. And so remember, you're going to divide all of your old x-coordinates by 1/2. So my x-coordinate right here is +1. Remember, the x-coordinate is how far left and right you are. So +1 divided by 1/2 is the same as +1 divided by 2. Shoot, try that again. +1 divided by 1/2 is the same as +1 times 2. And +1 times 2 is 2. So this point goes right here. This point has an x-coordinate of 0. And 0 divided by 1/2 is the same as 0 times 2, which is just 0. So this point is going to stay right here. Note that I'm not affecting any of the y-coordinates. I'm just moving things left and right because I'm just affecting the x-coordinates because I have a horizontal stretch going on here. This x-coordinate, how far left and right it is -1. And -1 divided by 1/2 is the same as -1 times 2, which is -2. This point goes right here. And so what my graph is going to end up looking like, I mean, I guess you can imagine there's another point up here that has an x-coordinate of 2 and a y-coordinate of 8. And so that point that has an x-coordinate of 2 and a y-coordinate of 8 on the red graph, its x-coordinate of 2 is going to get divided by 1/2. And 2 divided by 1/2 is the same as 2 times 2, so that's going to go out here to 4. So this point that was roughly here is now going to be out here, and maybe that helps a little bit when you're trying to get the shape of this thing. It's going to look, roughly speaking, not a great graph, but hopefully close enough, like this. Yeah, this is kind of bad. Let's make it look more like this right here. It's hard to draw on a computer, but hopefully that's close enough for our purposes. This would be g of x equals 1/2 x cubed. A comment I want to make is the same comment I made when I was up here. What most books will tell you is if the value of b is between 0 and 1, then you have a stretch. If the value of b is greater than 1, then you have a compression, kind of like we had up here. There were different cases. Some were stretches, some were compressions. Up here, when the value of b is greater than 1, you have a stretch. Down here, when the value of b is greater than 1, you have a compression. So that's really confusing too, keeping straight which one you're doing in what case, and it's even worse if b is negative. If b is negative, then you have to worry about there's also this reflection idea going on, except instead of reflecting over the x-axis, we're going to reflect over the y-axis. Oh my God, I'm never going to keep this straight. Yes, you are, because you're not going to think about it in terms of these. You're not going to think about this in terms of compressions or reflections. You're instead just going to keep straight the operation. So, for example, if I asked you to sketch a graph of, I don't know, h of x equals, let's say, negative 2x to the third power. Oh man, what the hell is that graph going to look like? Well, if you're thinking in terms of these names, it turns out that you have two horizontal transformations going on. You have a horizontal compression and a horizontal reflection. But you don't need to know that. All you got to know is that playing the role of b in this case, that first recognize we're in this column, and playing the role of b in this case is the number -2. And as long as you can divide numbers by -2, you can come up with what this graph looks like. Start with our red graph. This point has an x-coordinate, left, right, of 1. 1 divided by -2 is -1/2. This guy's going to go right here. This point has an x-coordinate of 0. 0 divided by -2 is 0. This point right here has an x-coordinate of -1. -1 divided by -2 is +1/2. This guy's going to go right here. Again, I have some point up here at 2, 8, because when I put 2 into this function, this red function, 8 comes out. So I have this point way up here at 2, 8, and its x-coordinate is 2. So when I transform it, I'm going to take that x-coordinate of 2 and divide it by -2. 2 divided by -2 is -1, so that point will be like right here. And maybe that'll help you sketch this graph. It's going to end up looking something like this. What you did geometrically is a mess. This is expert level stuff that you just did geometrically. You flipped this thing over the y-axis and you compressed it all towards the y-axis. Damn, that's a lot. And it's a lot to keep straight just seeing this example and knowing how to do all this. And guess what? There's even more. We still haven't combined these different transformations. And so I think if you're thinking about it in this column, it's almost impossible to keep everything straight. But if you're thinking about this column, that wasn't that bad. I just divided everything by -2. I recognized that I had this type of thing because the -2 was getting multiplied by the x, not the x cubed. I recognized that I was in this case and I divided everything by -2 because playing the role of b was -2. That's all you got to do. I'll give you 2 more examples. If you can, this is as hard as this stuff gets. This is expert level stuff. We start out with whatever graph you want. Let's start out with our standard parabola, f of x equals x squared. You know what? I'm gonna give you something even harder than that. You're like, slow down. You don't need to make this super hard for me. So this graph, you have this kind of semicircle looking thing here, and then I got this. I don't know what the equation of this graph is. In fact, I'd have to define, well, that's not true that I don't know, but let's suppose that I don't know. I'd have to define it with a piecewise function. It would be really messy to come up with an equation that represents this function right here. But that's okay. Let's just call it f of x. And let's highlight some points on f of x. I got this guy, I got this guy, I got this guy, and I got this guy. This is my graph f of x. Suppose I asked you to sketch a graph of g of x equals 2f of x minus 1. Whoa. What's going on here? Okay, there's two different transformations going on in this case. And note that I can't put them into a function because I don't even know what this function is, so I have to write it in this more general form. But what I want you to be able to do when you stare at this thing is recognize that this 2 right here is similar to playing the role of b right here, because it's getting multiplied by the f of x, not by the x value. This 2 is multiplying by the f of x. And then I got this minus 1 right here, which is really similar to this. What I have in this case is my first 2 types of transformations. I have what your book would refer to as a vertical shift and a vertical stretch. Wow, that sounds like that's going to be really, really hard to deal with. And it is, and you can write this in multiple different steps, but I think if you follow this column, you can do it pretty easily. Note that this 2 right here is the A. No, that's not true, it's the B, because we're multiplying f of x by 2. And so all I got to do is remember that that means multiply all of my old y coordinates by 2. And this minus 1 right here is the A. So I'm going to add -1 to all of the y coordinates. And it turns out it's really important the order I do these in. And because these are both vertical transformations, I'm going to do the multiplication before the addition. I'm going to think order of operations, PEMDAS. I'm going to think multiply first, then add. So I'm going to take all of the old y coordinates. I'm only messing with the y coordinates because these are just vertical transformations. And what I'm going to do is first multiply the y coordinates by 2, then subtract 1. So this point right here has a y coordinate of +1. If I multiply +1 by 2, I get 2. If I subtract 1 from 2, I get back down here to 1. This point is going to end up right where it started. This point has a y coordinate of 2. 2 times 2 is 4. 4 minus 1 is 3. This guy's going to go right here. This point right here has a y coordinate of 1. As we saw before, 1 times 2 is 2, but then -1 brings me back down to 1. This y coordinate right here appears to be, I'm going to put another point in here so I can track these better. This should be in red so I don't confuse people. This y coordinate right here has a height of 3. Right, the y coordinate is 3. 3 times 2 is 6, and 6 minus 1 is 5. So this point is going to move way up here. And then this one right here has a y coordinate of 5. 5 times 2 is 10, minus 1 is 9. So this guy's going to be way up off my graph somewhere up here. But I can connect the dots with something that has roughly the same shape as the initial graph. And end up with my graph of g of x. That's expert level function transformation. Because what I just did there is multiple transformations all in one. Let's do one more of those. How long is this video getting? It's getting pretty long, but I think function transformations is one of those things that demands a lot of time. So let's start out with, what should we do here? Let's do this same wacky looking graph. So I start out with a point here and a point here and a point here and a point here and a point here. So I'm going to start out with this strange looking f of x graph. And I don't have an equation for it, but that's okay. I'll just call it f of x. And what I'm going to try to do now is figure out g of x equals, I don't know, how about f of 2x minus plus, I mean, I guess it doesn't really matter, plus 2. Let's see what that ends up doing. I don't like using 2's twice. That might confuse people. 2x plus 3. Sure, I can do that. So I want to graph some function that starts out with this as my base function, but then applies these two transformations. This 2 right here is this one. This 3 right here is this one. I knew they were both horizontal transformations because they were both affecting the x, not the f of x. They're both inside the parentheses. That's not a great way to think about it, although that's true. But it's because you're affecting the input to the function. They're making these changes before it goes into the f machine. Okay, so over here, I remember that I was supposed to multiply first and then add or subtract. I followed my order of operations. But wait a minute, you told me earlier that everything with horizontal transformations is goofy. Everything goes backwards of what I'd expect. Is that still going to happen here? Yep. Okay, so if everything is backwards from what I expect, then I guess I would apply this transformation first and this one second. That's true, and it's important that you do that. So I am going to always, maybe I'll even put in a note here, I'm going to apply this one before I apply this one, but I am going to apply this one before I apply this one. This is kind of the order. You might have a question at this point. You might be like, yeah, wait a minute, what if you have vertical and horizontal? The nice thing is that if you have vertical and horizontal, the order that you apply the verticals versus the horizontals makes no difference. So you can do all your vertical stuff first, then all your horizontal stuff, or you can do all your horizontal stuff, then all your vertical stuff. Just note that if you have multiple vertical transformations, you have to apply them in this order. If you have multiple horizontal transformations, you have to apply them in this order. If you just have one vertical and one horizontal, apply them in whatever order you feel like. You'll end up with the exact same graph. We don't have that here. In this case, we just have two horizontal transformations, so I want to apply this one first. So what's playing the role of A here? Well, it looks like positive 3 is playing the role of A. So what I am going to do is I'm going to subtract 3 from all of my x-coordinates, and then I'm going to divide all of my x-coordinates by positive 2. So I'm going to subtract 3 and then divide by 2. Let's see if I can do that. My x-coordinate right here is negative 1. If I subtract 3 from negative 1, I go to negative 4. If I divide negative 4 by 2, I go to negative 2. So this point's going to end up right here. This point has an x-coordinate of 1. If I subtract 3 from 1, I get to negative 2. And then if I divide negative 2 by 2, I get to positive 1. Sorry, negative 1. This point has an x-coordinate of positive 3. If I subtract 3 from positive 3, I'm at 0. And 0 divided by 2 is just 0. So this point's going to go right here. This point right here has an x-coordinate of 4. 4 minus 3 is 1. And 1 divided by 2 is 1/2. This point right here has an x-coordinate of 5. 5 minus 3 is 2. And 2 divided by 2 is 1. So these 5 points will move to these 5 points. And if I connect these points with a graph, I end up with something that looks something like this. The geometry of what I just did is very, very complicated. But that's okay. I don't need to be able to describe the geometry as long as I can just go through all the different operations. This would be my graph for g of x. These last two examples probably shouldn't come in an introduction video because those are really, really hard. If you were following me with the first 4, that's fantastic. That's way beyond where you should be right now. Maybe you'll end up watching this video a couple of times. That is all of the different transformations, which is 90% of this section. The last thing I want to talk about are odd and even functions. We'll move this down to the next page here. Odd and even functions are related to transformations, but they're not quite the same. Maybe I'll make a little chart here. Odd function, even function. I want to be able to describe these things algebraically, and I want to be able to describe them geometrically. Algebraically, geometrically, whatever. This is in an English class. And then I want to be able to maybe have an example of them. How about, yeah, let's just do example. Sorry for the bad handwriting. In order to be an odd function, algebraically, you must satisfy this criteria. Wait, what does that mean? Let me write that so it's easier to see. It must be true that f of negative x equals negative f of x. Note that I deviate from your book again here. Your book will say the negative, it'll multiply both sides of this equation by -1. So this negative isn't here, it's instead over here. I think it's easier to write it this way, and I'll explain why in just a second, but this is equivalent to your book's criteria. An even function algebraically is similar, except now f of negative x, the same thing that I'm going to test, is not equal to the negative of f of x, it's just equal to f of x. Wait, what do you mean? Don't worry, I'll get there, just a second. Geometrically, this has to be symmetric about the origin. Wait, what origin? What do you... Slow down, I'll talk about it. For an even function, there's also some symmetry, but now it's not about the origin. Now I'm going to be symmetric over the y-axis. Example, x cubed, x squared. Hey, 3 is an odd number and 2 is an even number. Coincidence? Not really. Although you got to be a little bit careful there. Okay, now let me go through and explain all this mess that I've been writing here. If you have a function, any function you want, let's start out with the function like f of x equals x cubed plus x squared plus x. That's a little much. How about x cubed plus x plus 2? This is a function. And I might ask you the question, is this function even? Or is it odd? Neither? We can figure that out. And you can figure that out two different ways. You could graph this function. Because if you have the graph of a function, you can determine whether it's even or odd based on this criteria right here and by looking at the graph. But what if you don't know what this graph looks like right here? What if you don't immediately know what the graph of x cubed plus x plus 2 looks like? Is there a way to figure out if this function is even or odd just algebraically? And there is. It's this test up here. And so, again, the reason I write this like this, which is slightly different from your book, is I can test for even or odd by testing the same thing. Determine what f of negative x is. I have f of x, right? This is f of x right here. So if I asked you to determine what was f of negative x, could you do it? I mean, think back to section 1.1. This is a blueprint for this function x, or f. And it's saying that if you put x into it, x cubed plus x plus 2 comes out. And based on this blueprint, you can figure what comes out no matter what you put into this machine. Put in 7, put in a plus h, put in anything you want, and you figure out what comes out. You could put in negative x if you wanted. All you do is copy this thing right here, except everywhere you see an x, you would replace it with the negative x. This right here is f of negative x. The question is, this thing right here, is this equal to f of x? Because if this thing right here is equal to f of x, then I have an even function. The answer to the question, is this the same as this, is yes, then I have an even function. If it's not the same as this, then I don't have an even function. Do I have an odd function? Well, to determine if I have an odd function, the question is this thing right here the negative of this thing? So maybe for reference over here, I'll say the negative of f of x would just be the negative of this thing that I just wrote, x cubed plus x plus 2. So when I'm determining whether this function is even or odd, what I do is I first figure out f of negative x. And then I ask myself the question, is this thing in green the same as the thing in red? And if the answer is yes, then my function is even. If the answer is no, then my function is not even. Then I determine, is this thing in green the same as this thing in blue right here? And if the answer to that question is yes, then my function is odd. If the answer to that question is no, then my function is not odd. That's all I'm doing. Unfortunately, it's a little bit hard to look at these things and figure out if they're identical. I mean, if you're really good with algebra, you might be able to figure out if they're identical. Really, all you have to, the best way to do this is to do a couple of these examples and sort of learn how to do this. Negative x cubed is the same as the negative of x cubed. And that's because you can think about this as negative 1 times x, and negative 1 to the third power is negative 1, and then x to the third power is x. So this, it's the negative x being cubed. Here, x is being cubed, and then it's multiplied by negative 1, and these are equivalent. Adding negative x is the same as subtracting x, and then I have this plus 2 right here. So I could simplify this thing in green and write it like this. And the reason I simplified this thing in green and wrote it like this is now it's a lot easier to see whether the thing in red and the thing in green are the same. In fact, they're not the same. This is not the same as this, because in this case I have 1x cubed and 1x. In this case I have negative 1x cubes and negative 1x's. This in red is not the same as this in green. Is this function even? Nope. How about this? No, how about f of negative x is not equal to f of x, so f is not even. And then I can do similar analysis over here. This thing that I simplified in green, is that the same as this thing in blue right here? Might be. I don't know. Let's see. Let's simplify this thing in blue. It doesn't look the same because this one has parentheses and this one doesn't. But maybe I could get rid of all the parentheses just like I did up here. I take this negative and I distribute it through the parentheses. I get negative x cubed. Oh, cool. Just like I have here. I'd get negative x. Oh, nice. Just like I have here. Oh, wait a minute. I get negative 2. If you take this negative and distribute it to all three terms, you'd get this, which is damn close to this, but not quite the same. And this is a case where close is not good enough. This is not the same as this. Green is not the same as blue. f of negative x does not equal the negative of f of x, so f is not odd. The specific example I gave you, the function is not even and it's not odd. It's neither. Had this been the same as this, then your function would be even. Had this been the same as this, then your function could be odd. Usually get the question, could it be even and odd? Yes, but only for really trivial functions. I won't even get into that. That's how you determine if a function is even or odd algebraically. Maybe you can check that this function x cubed satisfies the odd criteria. What would f of negative x be equal to? What would the negative of f of x be equal to? What would the green thing be equal to? What would the blue thing be equal to? Maybe you convince yourself that green and blue would be the same for this function. So for this function right here, I guess if I'm going to call it a function, I should write it in function notation. This is an odd function. And this right here is an even function. And the reason this one was neither even nor odd is this is to the third power and this is the first power, which are both odd, which would make you think the function's odd, but it's not because of this plus 2 right here. This messes stuff up. So it's not as easy as just looking at the exponents and determining whether they're all even or odd. It gets a little bit screwy, especially if you have fractions and stuff and constants going on. So really, there's no shortcut around checking whether things are even or odd. You just go through this test algebraically. And there's another way you can do it. You can graph these things. I can take my function x cubed plus x plus 2 and look at what the graph of that function looks like. So let's look at what the graph of that function looks like. X cubed plus x plus 2. Let's graph this guy. Make sure I typed it in right. Take a look at the graph. There's what it looks like. Kind of looks like our x cubed, but it's shifted a little bit and then also shifted up. This is what the graph looks like. The criteria for being an even function, which is what I have in this column, is it has to be symmetric over the y-axis. The y-axis is the axis that goes straight up and down. And what I mean by symmetric over is if you think about this as kind of a mirror, if you took this thing and reflected it over this line right here, would it land right on top of itself? So what I'm going to do is I'm going to sketch a graph of this, maybe down here. I had this thing that, roughly speaking, looked like that. That's a horrible drawing, but I think it'll be close enough for our purposes. Here is f of x equals x cubed plus x plus 2. This is what I got off this graphing calculator. Something like this. If you stare at this thing right here, you can ask yourself, is it even? It's not even. The reason it's not even is because if I reflect this thing over the y-axis, I'd end up with this graph right here. And the blue dotted line did not fall right on top of the red line, so it's not even. What about odd? Can you check odd just from the graph? Yes, although it's a little bit weird. I prefer to think about it as symmetric about the origin. There's another way you can think about it, but let's start with symmetric about the origin. First, know that the origin is this point right here, 0, 0. So the idea about being symmetric about the origin is, can you take any point on this graph in red and sort of bounce it over the origin and have it land back on the graph? So if I took this point, for example, and I kind of bounced it over the origin, it would land way the hell down here. And would that be on the graph? Well, it's kind of hard to tell. Looks like it's possible that it could be, but I can't really tell. Yeah, but what about this point right here? If you took this point right here and you reflected it about the origin, it would land somewhere down here. And this point right here is certainly not on the red graph right here. So what that means is the graph in red is not symmetric about the origin. So this thing is not odd, as we decided already algebraically. If you don't like this idea of bouncing things over the origin, which is a little bit weird, you can also ask yourself the question, will the red graph land on itself if I first flip it over the y-axis and then flip it over the x-axis? Okay, if you took the graph in red and you reflected it over the y-axis, it would land on the dotted line in blue. We already did that. And then took the dotted blue graph and reflected that over the x-axis. Well, let's see, this point would be down here, this point would be here, all these would be way down here. I'd end up with a graph that looks something like that. It's not the greatest picture in the world, but hopefully that's enough for you to see that the green dotted line is not the same as the red line. So again, it's not odd. If I confuse you with that last one, don't let me confuse you. I think it's easier to check the odd, to check whether a function is odd, to bounce all the points over the origin. But just so you know, if you don't like bouncing all the points over the origin, you can also reflect it over the y-axis and the x-axis. And the question is, what you end up with, would it land right on top of what you started out with? And the answer is no, so therefore it's not odd. That's a quick summary of even and odd. And then function transformation quick summary. That's a hell of a long summary. Probably time for me to stop this video.